So, hello everyone. Welcome to Deep Dive into Silverlight 3 graphics. So before I get into our slide deck, I want to talk about an application that is enhanced with graphics and something that we want to keep in mind when thinking about how to use these new features. The question is, how do you actually enhance an existing application? So, designers are often asked to display a music collection. And the particularly weird problem about music collection is albums are square. And they need to be presented in a 2D space. Well, they end up taking a lot of space if you want to go, if you want to take up some vertical height, you're going to actually show less. So one option is to sacrifice, in order to show more than 3 albums for those who have more than 3 albums in their collection, one option is to actually shrink down the size. And squares, of course, you shrink down vertically as well. And so we're beginning to see more and more applications start to switch from 2D to 2.5D. And what we do here is we're actually able to still have the height. We're still able to use that much real estate and still able to actually show that many more albums. Of course, the problem here is that I really don't know where my user is looking at. And so what Apple did with iTunes was that they went ahead and they said, OK, well, I actually want to dedicate the most real estate to the selected item, the current album that's playing. And then the items on the periphery, I'm going to sacrifice the amount of real estate that we dedicate to them. So now I know I have a vanishing point. I have more real estate dedicated to one item. And this is actually a list box of some sort. So afterwards, they went a step further, and they added a reflection. And the reason why this reflection isn't just completely gratuitous, which some of us tend to think of graphics features as, is that they went ahead and they had the same album size. This is the same album size that was shown in 3 of the 5 slides that you just saw. They have that amount dedicated to the selected object. And then they went ahead and added a reflection, which enhances by almost 1/3 of the real estate that you dedicated to that selected item without sacrificing the aspect ratio. And that's a simple way of enhancing the amount of real estate that you're presenting 2D square flat objects. Now you have perspective, a vanishing point, and reflection. And all three of these are opportunities to enhance your graphics application. And they are all available in Silverlight 3 beta today. So hello, everyone. My name is Seema Ramchandani. I've been working on graphics and perf in Silverlight for about 2 years now. And prior to that, I was working on WPF. And when thinking about what graphics features that we were going to create for Silverlight, we wanted to focus on the key customer adoption blockers, the scenarios that were not possible in Silverlight 2. And so we went ahead and we enhanced 4 aspects of our graphics pipeline. The first one being how we draw. And I'll talk about that in depth. It's important to understand exactly what's going on in the pipeline behind the scenes. The second one is we added effects, also known as pixel shaders, to Silverlight. The third one being projection, the 2D to 2.5D, a simple way of actually enhancing your application with 3D concepts. And then we started to harness the GPU to enhance the performance of Silverlight. So let's start with how we draw. When thinking about how we draw, it's always important to understand where your user code is executing versus where everyone else's is. So there's one UI thread per browser, and that's shared between all the plugins that are actually available. So if you have multiple plugins on a browser, remember that, remember your nanoseconds, remember how much time you're actually taking. So the user code, our layout code, our animation is all running on the UI thread. And so if you're actually running something complex, it's going to sometimes pause your animation, and that's simply an understanding as to why that's happening. Off of the UI thread, we have the frame rasterization, media decoding, and of course, the things that we're harnessing the GPU for. So we have this loop, and it looks like a complex loop, but it happens 60 times a second on Silverlight. So the first one is event handlers. Anytime that your user is interacting with the application, they're going to probably incur an event. It's almost like the muscle movements of your application. So we go ahead and we interact with the event. We run some user code. And by the next time that there's a tick, which happens at 33 milliseconds, the default is 60 times a second, we go through and we say, hey, are there any property changes? And now one of the key ways of changing properties is by a double animation. You can have this in your state transition, like you click, you animate your opacity, et cetera. That's the key way that we animate. When evaluating animations, it's important to understand how Silverlight thinks about what the property value is at that point in time. And the way I think about it is we're a real-time based system. So if, for instance, we're at the second frame, 33 milliseconds, and then the UI thread gets a little busy, does some other things, and we skip 3 frames. In a frame-based model, this would mean that we would continue at the 3rd frame. We would continue where we left off. Silverlight is actually a clock-based animation system, and so we continue where we actually expect it to be if we had looked away and continued running that film strip. So we identify what the property values are at that point in time. So in the example before, it was projection. We evaluate what it is at that point on the clock. And then we run layout. Now, the animation and layout system, all of our property system, is built on our tree model. And what we did in Silverlight 2 was we walked through and did a poll, like an actual poll of all animations active in the system, and we checked to see if any of them were dirty. And it was okay if you had like 600 animations and most of them were inactive. But we started to notice that if you had more like 10,000, 20,000 animations, because you have a list box, each list box item has 6 items, it gets a little bit more complex. And we started to see that if you had one active animation, we were walking through the entire tree, checking to see if any of them were dirty. And so in Silverlight 3, not in the beta, but actually in our RTM code already, we're changing the model from a pull system to a push system. And so the dirty regions has been updated. So that's one perf benefit to see in the upcoming changes. If you have one active animation and a lot of inactive, you don't pay that cost anymore. So we walk through the layout system in 2 passes, a measure pass and then a arrange pass. And that basically, the first one is, well, I don't know what size I want to be. I first need to check the size of my children. Walk down through. They check, my children check the size of their children. Complete recursion. And then we go back and say, okay, well, here's the size that you get, and apply a clip or transform as needed. The system is designed for nesting. And keep that in mind for those who are control vendors. Who's a control vendor? Who writes controls for other third parties? Okay. So in the situation where you don't know what panel you're going to be actually hosting your control in, you're often going to have the situation where you might not actually need to rearrange your children inside. And so you can opt out of responding to layout. So Toolkit is publishing a bunch of different layout panels like wrap panel or dock panel or animating wrap panel. All of those, you can opt whether or not to react to those layout passes. Layout impacts render calls by 2 main properties, the layout clip and the local transform. And so here I have actually set the width on my child, on the button, and applying the clip because it's now bigger than the box that it's allotted, and then the offset. Pretty self-explanatory. Both of these are consumed in all of the places that you expect to. We're not going to hit test things that are clipped out. Okay, so now we have layout, and then we queue up all the rendering changes. The key thing about Silverlight is that we actually, when we're stitching together the scene at that frame, we analyze what all the property changes are at that point in time. We don't rasterize them individually. And then we identify how to stitch all of those changes together, and then we give the browser the frame to actually present. In hardware, this would be actually handed to the GPU to actually present. So this is all basics here. So we start off with rendering the children. And it's important to know the order of events in which we draw, because we're going to get to the more complex features later. And you want to know why they work in a certain way. So we start off with all the children. We then apply the opacity mask, then the opacity. We then apply the clip and the render transform. Notice that the opacity is applied before the clip. That means that you might be actually spending blending cost on something that's actually not even viewed. We apply the layout offset, and then all the parent properties. This is how we draw. This is an order in which WPF draws as well for rendering parity. And so, again, minimize the number of size of affected objects. And I'll get into this in the perf talk tomorrow. Well, we'll skip that for here. So we have this set in Silverlight 2, and then we enhance it with the 3 features of Silverlight 3. And the main features is we do a hardware cache at the base, which allows us to hand at the very basic what this surface looks like, and then ask the GPU to apply all of the properties above. And I'll talk about that in a second. And the effects and the projection. So how do we actually do this? All 3 of those properties, all 3 of those concepts work on an intermediate surface. So we render into an intermediate surface, which means that we create a buffer that's of the size. This is in memory. And then we hand that, let's see. We create the buffer, and we render directly into the intermediate surface. And then on that intermediate surface, we'll actually apply the effect or the projection, what have you. And then we go ahead and, if there's a second effect, then you're going to actually create a second intermediate surface, and there you go. So the key thing here is the amount of properties that you're applying. You might see memory size increase, and you might also see the amount of time that it takes to do all these blits will actually increase. So it's important to keep these in mind when using these 3 features. So we talked about 3 of these features that use render to intermediate, the 4th being writable bitmap. Writable bitmap is basically take what's in the pipeline and blit it to the screen. And so we, again, use the intermediate service to identify what that looks like. Let's talk about effects. So Silverlight has 2 types of effects that you really want to think about. We have the built-in effects, which we wrote because they're multi-pass, and Silverlight doesn't have a simple way of doing multi-pass shaders within Silverlight. And so we wrote in the blur effect and the drop shadow effect, and they're pretty easy to use. Button dot effect, add a blur. And then we have the custom effect, which is composed of 2 components. The high-level shader language file, HLSL, which is compiled into a binary that is invoked by the .NET class, a regular old C# file that will invoke the shader and set all of the properties onto it. And the great thing about effects is that they can pull content from anywhere within the scene, anywhere within your application. So let's talk about the .NET file. Silverlight's shader engine allows for quite a few variables to be inputted. We allow you to register at least up to 16 brushes, so we allow for multi-input, and 32 constants, doubles, floats, colors, etc. We then invoke the compiled version we support of the HLSL file, and it's compiled via either you can do it via the DX SDK, which, by the way, is 500 megs. I tried to download it at a coffee shop. Didn't work out so well. And a WPF build task, which is more like, I think, 2 megs. And that's what I'm going to be using in our demo today. I'm going to go into shaders, but here, Greg Schechter was our architect for WPF and Silverlight for quite some time, and he wrote a great series of blog posts on pixel shaders, how they work, and how they run. The only difference being in WPF, they're in hardware. But I would check out his blog. Okay, so one of the PMs on our team, who was actually the author of our shader spec, wrote a simple invert shader. And we'll go ahead and write this today. So When building a shader app, I'm going to start with a pre-built application. I've just edited their targets file and added a little bit of XAML. So I'll walk through that today. Mainly, I have a stack panel, 2 stack panels, which have the same thing in it, a tree and an image of a tree and a button. And so what we're going to do here is we're going to create a custom shader using the WPF templates and then integrate it into our Silverlight application. So to begin with, I'm going to add a class. And I've installed the template already. And so I'm going to use the default template for WPF shaders. And we want to build here a shader, an invert shader, so I'll just call it that for now. This class was written for WPF, so there are 2 changes that I need to make by default. I need to change how the URI is created, so let me just go do that. So this is where I specify where to find the compiled version of my pixel shader. And then I need to just specify the, let's see. OK. The second thing is just a minor edit. So I hope to fix this in the template later. We'll have a Silverlight template posted. OK, so that's now my application actually compiles within Silverlight. The Silverlight template, the WPF template creates the .NET file and then the HLSL file. And by default, it takes in 2 properties, a color property and a brush of the effects that I'm applying, a brush of the element that I'm applying the effect on. And then it basically says, the color that you gave me, multiply it. So I'm basically just doing a color filter of the shader, of the brush. When I compile this app, I actually want it to be viewed. Let's see, why isn't, OK. I want it to compile as an effect. This is available with the minor targets edit that I had made earlier. And now I want to actually apply it. So I've specified my namespace to be this application. And I'm going to apply my effect directly. Oh, we got some alignment problems. OK. And so we have 3 options. Whoops. We have the blur effect, the drop shadow effect, and then, of course, the one that I created myself. OK. So I'm going to first build it. And what this does is it actually compiles for the first time my FX file into the pixel shader compiled format. And to pull this, I'm just going to do I know there are experts in VS who can do this automatically, but I'm just going to drag and drop it. So now I'm actually included the PS file that's compiled from my FX, from my HLSL pixel shader, directly into my application. And I'm going to mark it as content. OK, so now I have, on the left, I have an element that is just a stack panel with a button and an image. And on the right, I have the same exact thing, but applied now with my pixel shader, which is doing a color blend with yellow. OK, so that's the default template. That's what WPF gives you by default. But we want to write an invert shader. So the only variable that we need to do the inversion of an image is actually the element that was given by default. And so generally in shaders, we have an implicit shader that's defined within Silverlight to actually be the element that's handed back, whether it be an image, a brush, or what have you. The implicit input sampler is actually a brush of the render to intermediate surface that we talked about earlier. So it's whatever element was rendered by default. And we're putting it into the first register, S0, of our samples. I don't need any other constants. I then look into my main pipeline. And my main pipeline, the input, is just what position we're calculating right now. Shaders, most graphics will use a UV mapping, which basically you just need to know that it works on a 0 to 1 scale. And it works into mapping a point within a texture, such as our implicit input, into what pixel color it is. And this is actually how all brushes work behind the scenes in Silverlight. They're basically a mapping of a UV coordinate into a brush. With a solid color brush, they all map into the same pixel, right? Linear gradient brush, they map into a 1D vector. Same with radial gradient brush. It's just a mapping of screen position to color. And then the image brush is actually the best way to think about the implicit input, is that whatever was in our render to intermediate, I'm just basically saying, hey, what color is it at this pixel location here? And so my stack panel is my brush, and it has buttons, and it has an image. So I find out what the color is at that pixel value. And then I invert it by just subtracting it from 1. I can do this a couple of different ways. There's optimizations. This is pretty optimized. You could do color.r, the red color equals 1 minus the red color, and then repeat it for green and blue. All of this gets compiled wonderfully by DX, so you don't have to worry about optimizing it too much. OK, let's go do this. So we have the default shader that was created by the template. I don't need the color filter anymore, so I'm just going to delete that. I don't need all of these comments either, so you can see everything on the screen. I still want to take the color that was originally there by mapping into the texture brush, and then I just want to do the simple mapping. So like I said, I could do this individually, or I can just manually handle it. The high-level shader language was written by DX. It's wonderful. You can read lots of wonderful docs about it. But the key takeaway here is that it is simple to use, and it's also very simple to copy other people's shaders. So here we go. Here's an inversion. It's very simple. The button is actually interactive, right? You can click on it just like the other button. And it's pretty quick. So there we go. We've written our first shader. Now, my guess is most of you guys will want to write more than just the basic shader app. Where is, oh, here we go. Reorders everything. When writing a slideshow, for instance, animating one image to another image, I want to do some sort of transition effect. And I've seen that WPF has done these, but like up to a week ago, I never knew how to write these with a transition effect, like an actual animating transition effect. And so what we did here was I said, OK, well, WPF wrote it. I want to copy and paste it into my own application. And so I'm going to walk through basically what you needed to do to compile and use this other pixel shader written by somebody else into your application. We're waiting for VS to come back. It's thinking. Oh, it's initializing the toolbox. That's great. OK. So the main thing here is we're going to take in 5 inputs into a transition effect. And I'll show you what this looks like in WPF. So I basically went through the WPF. WPF has a little bit of a catalog of transition effects that are available today. And they have all sorts of wonderful little transition effects that you can do and integrate into your application. And so I saw this one, and I thought that that was pretty fancy, and I'd like to use it. So the effects library is available directly into WPF. And you can search out all their code, and they completely welcome you to write your own, to use the effects and to harness it within your own application. So you have the CS files, and you have the shader source. So basically, the cloud reveal, pass some HLSL, and now I'm going to integrate it into my Silverlight application. Yes, question? For the pixel shaders are written in HLSL, which is the same language used between WPF and Silverlight. And so it is possible to copy and paste the HLSL between the two. They compile out to the same. In fact, you could just drag and copy the PS file if you needed to. OK. So basically, what we're doing here is we have the same. Let's see. We have the same application that we had earlier, but this time I'm actually adding in a rectangle. And the rectangle has an effect that takes in one brush, which is the image that I'm animating from and the image that I'm animating to, and actually a progress property. So I'm going to just start it off without an animation just to see what's going on. This cloud shader is invoking the cloud shader class. Cloud shader class has 5 different properties, specifically the input that we're giving it. We're not going to use the default implicit input anymore. We're going to actually use one that we've specified within the property values. The second input, our cloud, which is going to be our mapping of how we apply the effect, and then the progress of where we are in time, and then our seed that goes back into the effects file. So now I've actually just copied in the HLSL from the WPF application. And by enabling it to compile and initializing it properly, we're actually able to use all of the effects library that we saw in the WPF application earlier. We're actually able to use it within our own app. It is not important to necessarily learn HLSL. You do not need to be able to code this in your sleep. This is something that we're going to largely expect developers to copy from the WPF effects library. OK, so now I've actually initialized it. And I've initialized it with a progress of 0.5. So I'm going to run. Oh, actually, I'm running the animation already. But what you see here is I'm animating in the progress property of this cloud transition. And it's taking in not one input, but 2 inputs. The background is actually just a rectangle, so I'm ignoring that altogether. And I'm filling in this rectangle with input from 2 different brushes, which are calculated out individually. Each pixel is interpolated based on the algorithm defined by the cloud effect. So I've enhanced this with a little bit of a progress animation. And the progress is just a simple double that is taken into account. And I'm putting in an ease, so like to give it more of an organic effect. So this is a simple feature that you can use within your slideshow or any sort of transitions that you want. And there's a full set of libraries that you can use within Silverlight and WPF today. Let's give it a second. OK. So we've written our effects file, done that demo. So we have 3 types of things to keep in mind with your effects. And when applying your effect, we apply the clip afterwards. And so one of the properties that you might need to engage is the padding property. So just looking at the docs, playing with it, allows you to go outside of the bounds of your UI element. And then let's look at those same features from a perspective. When we actually invoke an effect, any type of effect, we use the render to intermediate surface. If you're not actually using it, like let's say at the very end of the transition you've already finished, you actually want to get rid of that intermediate surface. And so simply just nullify it out. We sample all the pixels within our blur and drop shadow. And that's a little surprising for a drop shadow, which we would think would be just the edge pixels. But it turns out that most of our UI is not actually round, not actually square. It's rounded rectangles, et cetera. And so keep in mind that size does matter. The more pixels that you have in your surface area, it does affect the time that it takes to do the drop shadow or blur or any of the other effects. The blur radius is basically how wide we sample. And this is true for all effects. The math is actually pretty easy. It's the pulling of all the different pixels around that's actually pretty time costly. So what a blur radius would do is it says, I want to calculate my pixel based on not just my own color and not just the color of my, like, you know, my buddies to the left and to the right of me, but actually a radius, if I was actually creating a circle around it. And as we actually, as we move out and as we increase the blur radius, we're actually sampling more and more pixels. Pi r squared, right? So, is it pi r squared? It's been a little while. So, basically what you need to remember is that pushing around memory is time costly. If you're writing your own custom effect and you actually want to know what the next pixel is over, there's a great variable called, I think, ddx, ddy. It's the second derivative, and it basically is an index of how many pixels correlates to what UV difference. And so it's a great, if you write HLSL, how many of you guys have written a pixel shader before? Okay, great. So for those that need it, it's available, and it's pretty easy to use. Okay. The last thing to keep in mind about the perf of effects is that effects do not cache their output. We apply the effect every time that a property changes above it. We're working to optimize this, but because if you change an individual pixel, because the brush can actually, every pixel within the effect might actually touch a pixel in your original shader. We don't do any sort of dirty regions, right? There's no way to actually do that smartly because we don't know what's happening within your pixel shader. So that can be expensive. So in Marshall's app, I'm just going to quickly run it. Where is it? There we go. He has a bunch of different shaders that he basically implemented. And then I'm off CorpNet, so we're going to get a network error. But when I click, we're actually going to get a perspective transform. You saw how swift that was and how smooth it was. But it was actually rerunning the entire shader on that image for every single frame. So that was around 60 frames a second. So just keep that in mind when you're building your applications. And that's why I sometimes suggest nullifying your app out. One way to actually cache out the output is by using writable bitmap. I should actually note, we're right now working on optimizing that out. So Jason and Federico, our two devs on the shader pipeline and the perspective pipeline, are currently working to make sure that we don't run the shader every time you change the perspective. But it is something to keep in mind when building your application. Caching your input is very important. And so one of the key customer blockers that we tried to fix in Silverlight 3 was the concept of caching out your output. So writable bitmap has basically 3 usage cases. So the first one is largely a way to replicate your content. You have a combo box and you actually want to show the selected item in 2 places more than once. You actually can replicate your content by rendering that element directly into your writable bitmap and then displaying it on the tree. This is a screenshot of Google Chrome. I think Joe showed another example of this. This is a way that you can actually enhance your drag and drop UI by rendering a thumbnail of the content that you're dragging around. So that's a great usage of writable bitmap. But then the second thing is if you're running something very expensive, like the shader before, you can actually cache the output of our rendering pipeline. And then in the RTM bits, not today's bits, you can actually save the output of your rendering and then save it back to the user. If you want to write like an offline app that does brightness or contrast changes, you can actually save that file and encode it back by hand, or you can actually upload it back to the server. So as long as you have authority to look at the image, we actually allow pixel access in RTM. And then pretty much for those who actually just want to draw whatever you like, I think somebody was telling me about an energy grid that they want to do some data visualization if you want to write your own ray tracer. People have been doing great things with paper and logo and Etch-a-Sketch for quite some time. So you could map out how cholera works or how cholera is spread or map out a wonderful graph. But basically, writable bitmap is whatever you want. It's a back buffer to the screen. So we bring you writable bitmap to actually present whatever you like. Oh, and of course, whoops, sorry. You can actually edit and render back into it. OK, so we talked about effects. We talked about how to write a custom effect. We talked about how to copy somebody else's better custom effect. And then we talked about writable bitmap. And now we're going to talk about projection. So Joe went through a considerable amount of projection. And I highly encourage looking at his talk yesterday, which is recorded. I closed IE. Let's see. So this is an application. How many of you guys went to Mike Harsh's out of browser? OK. So for those who haven't seen this demo, it's connecting. It's on wireless. Oh, I guess, yeah. Mike wrote a wonderful little application, which is a slide builder tool in Silverlight. And you can import your slides, but I think the main thing here is let's just vary the colors a little bit so that you know what's going on. And traditionally, when looking at slides, the transition effect is mostly a blend. And Mike went one step further, and he said, well, how can 2.5D actually enhance this application? And so if you hit next, he's actually doing a projection of the two planes and animating them on their, I guess, the rotation y, on the y-axis to actually animate in and out of the different slides. So the code and the application are available publicly on his blog if you want to check it out. And in Joe's talk, he went largely through the projection APIs. We're pretty short on time, so I'm going to skip that. But largely, what I want to talk about is how projection works with the rest of the rendering pipeline. So two properties I want to highlight, basically. If you did a global offset, it would be basically on the z-axis. I would probably be taking a step further. A local offset would be something more like I'm working on the plane of my current projection. So if I'm at this oblique angle, and then I take a step forward, this would be a local offset, right? It's the difference of working within my projected plane or the global plane. And then the way they work with layout is largely the layout clip is applied before, but the actual z-index properties and the layout offset are applied afterwards. So what this means is you can harness the z-index to overlay and draw in a certain order the different projected children in a specified order. And so Joe went through all of the other properties within projection. I highly suggest looking at his talk for more examples. Let's talk about hardware. OK. Hardware is near and dear to my heart because I worked on WPF, and I saw a number of great ways that you can harness the GPU, but I also saw some things that were more of customer blockers with harnessing how complex it was underneath the scenes. And so what we wanted to do in Silverlight was we wanted to start simple. And basically, what we do is we take a cache of the element after it's rendered, but before any of the above properties are applied. Which means that later on, we can actually start to enhance that intermediate surface by having the GPU apply any of those properties. And in Silverlight 3, we started with just 3 of those properties. The render transforms, the rectangular clipping, and the blending are offloaded to the GPU. And this is mainly for scenarios of slideshow, actually animating in and animating out images, and doing things like stretching video. In fact, our P0 was just largely stretching video. So the impact that hardware has on an application is pretty robust. So this is two images that are basically shrunken and then animated with their opacity. And in the software case, this is going to be taking around 15, 16% of my CPU. If I had actually a higher resolution, I was seeing around 20, 28% CPU. So, so in software, this is actually taking time because I'm not only doing, I'm calculating what the opacity is, and then I'm doing the blend, and then the calculation of what each pixel looks like together. In hardware, you see the CPU basically drop down to around 2% because all we're doing in the software is calculating what the property value of that opacity property is, and then we're handing off the blend operation to the GPU, and so that's essentially free. And so all we're doing on the CPU is calculating the property change. So how do you harness hardware in your application? Let's first keep in mind what we can actually hardware accelerate. We start off with the hardware cache. We allow you to hardware accelerate the opacity, a rectangular clip, not all clips, the render transform, and the layout offset, which is a type of transform. But opacity, mask, effect, and projection were all written with software-only pipelines in Silverlight 3. And in Silverlight 4, Silverlight 5, maybe we can get into hardware accelerating those as well. But at the beginning, what we wanted to do was start small. If, for instance, that you have an opacity mask or effect or projection on that hardware surface, what that would mean is we would do the opacity, let's say that you're doing an opacity, we would do that blend on the hardware, and then we would blip back to the software. And that can actually get expensive, shuffling back and forth between software and hardware pipelines. And so and it actually can do more damage than good. So if you have effects or projection or any other software-only code path above the cache point, we fall back to software. And that's something to keep in mind when you're debugging your application, wondering what's going on. So the way to get hardware acceleration is to start by actually setting it in the plugin before the plugin surface is created. The enable GPU acceleration property, which creates and allocates a buffer in the video memory the size of your plugin, basically something to do the final blit on. We then individually, by hand, can set any of our unique elements for caching. And the caching that we do is basically a bitmap cache. We're not talking about vector graphics here. We're just talking about if you take a button and you stretch it, it's going to be that button, an image of that button stretched. That can be very quick, and it can be advantageous at times. For media images, this is a great thing, because basically we're just taking a cache of the bitmap of what it looks like, and then handing it to the GPU to do the basic behavior of transforming it, blending, and clipping. And so a great example is media shrinking or stretching. The support for Silverlight hardware is in browser and full screen on Windows for any DX7 hardware. DX7 hardware, I think, let's see, that correlates to probably pre-2004, probably XP, I think, timeframe. And it's all DX9C drivers, so you actually have to have XPSP2 or above. I think one thing to note, we are not supporting Windows 2000. On the Mac, we support hardware in full screen due to a couple of different browser compatibilities with the pipeline. So trying to decide whether to use GPU, you basically want to identify, are we stretching, are we doing a clip, are we doing any of those properties? Are we affecting any of those properties at a certain point of time? And so if yes, then we actually want to walk through our code and set the properties. I'm going to walk through an application that I have from Silverlight 1.0 and enhance it with hardware. in a second. But why not set everywhere? The key thing here is intermediate surfaces can be expensive. I've talked about this before, but when you offload to the hardware a surface that might be in the middle of your application, we're not only creating a surface for that item, but one for the front and the back. So we create two intermediate surface targets, which you can visualize with the debugging setting, enable cache visualization. And so creating, let's say, 100 cache nodes, you would actually end up creating 100 surfaces plus the ones in between. You don't want to ever nest these guys. So you definitely want to set hardware if you're stretching video. If you're doing any sort of adaptive streaming, et cetera, you definitely want to turn on hardware. If you have hardware already turned on, definitely set it on media elements for some minor nuances in the tree. For debugging, you actually want to turn on this enable cache visualization, which will allow you to see exactly what intermediate surfaces are created. And it enables you to sort of understand how much video memory and memory you're using. And then again, you only want to set it on leafmost nodes, not nesting, caching, and uncaching nodes. And of course, only set if there's user detectable impact. I think most of us like to get a new API, play with it, set it everywhere. And it actually does have a huge impact for all of the creation of those surfaces and then the blitting of those surfaces to other locations. OK, so how many of you guys have used XPerf for profiling? Oh, come on, you guys are in a graphics talk. You're supposed to know how to profile. So XPerf is a tool that was used or written by the Windows performance team for analyzing what's going on behind the scenes. And essentially, you want to keep in mind that we're going to be able to walk through all of the stack. I'm going to just go on the high level of how much CPU cycles is IE using. And I have a great blog post on how to use XPerf, which you can look up later if you ever need to. Where's my app? Halo. Where's Halo Player? There we go. OK, so this was an app originated from Expression Encoder 1.0. Sorry, 1 second. Oops. BI, OK. There we go. Let's get out of that. OK, so the way this app was written was with JavaScript, outputting a file that would basically create your Silverlight object within the, let's pause the video, within a create object X call. Over here, we're going to actually set the enable GPU acceleration to be true. I'm going to just show you the app with it false. And let's look at how the perf changes over time. So if I wanted to profile this application, if I wanted to actually see the difference between it in hardware versus in software, we basically want to measure what it looks like over time. So I'm turning on the XPerf profiler, and then I'm going to kill it and have all of the output, all of the event logs, outputted into a file which we'll call software2.etl. OK. What this allows me to do is visualize what cycles are spent, when and where, decoding this video and actually stretching it. The great thing about the expression encoder templates is that they resize to the size of your screen. They also go into full screen. Oh, maybe not. It's an old app. And they basically will be stretching your video at all times. If we enhance this with hardware instead, I'm going to turn on two features, both the enable GPU acceleration and the enable cache visualization, so you can see what intermediate surfaces are created. And I relaunched this application. You'll see first that I'm creating a surface for the items behind the video player. The video player is cached itself. The media element is cached. So there's, in tinted in red, is everything that's going to be an intermediate surface for the behind the scenes. And then in green is the surface that was generated for the stuff in front. And so you can actually see where intermediate surfaces were created. If we profile this application, we're doing, at this point, the application is just doing a stretch. Oops, sorry. I'm running the same application, but this time it's hardware accelerated. And I take a second ETL file, I take a second log in hardware, and then we're going to actually compare the CPU usage between the two. And so we'll let this run for a bit. Or we could do the Martha Stewart thing and pull out the already created ETL files. OK. So now I'm going to look at, let's see, the first one was called Software 2. So we're taking up, it's not huge, right? Like, our software media pipeline is pretty awesome. But if we instead did the hardware stretch instead of the software stretch, you can actually see a gain of quite some amount. To look at this even breakdown, we're spending about 22% of the CPU on IE stretching it. I'm going to show you this in higher resolution because it makes a big difference. So now we drop down to 7% CPU. So what basically I've done is actually dropped out the cost of the stretch. In a higher resolution monitor, it doesn't make that much of a difference for the low resolution we're projecting right now. But so natively, if I was natively showing this application, the hardware was about 12% of my CPU. Now, lots of things named Halo. And the software was actually around 50% of my CPU. And so actually we saw a drop of around 25%. The more that we stretch, because you have a higher resolution monitor, what have you, the more expensive that the stretch is going to be. And so if you hardware accelerate that stretch, you're going to see more of a gain. The takeaway here is the gains that you're going to see in hardware are largely dependent on how your application is built. OK. And so I did some profiling on my own machines with the resolutions that I use at home. Well, sort of. The first laptop was basically the crappiest laptop that we could find in the team. So it's a 1.3 gigahertz single core. I didn't even realize that they made these in 2004, but they do. And it was stretching the video at 70% CPU. If I took that same video and stretched it to full screen with hardware stretch, I see about my CPU usage drop in half. And this actually is consistent in all the ranges of CPUs that we saw our customers use. So as performance PM, I largely thought that the 2.4 gigahertz machine was a high-end machine, and the 1.3 gigahertz is largely your average usage. So you can harness the GPU to enhance your video playback within Silverlight. Now, let's say that you were actually taking the video and you instead had a larger video, in which case the encoding would be more of a cost. Sorry, the decoding would be more of a cost. Then the gain that you see by hardware stretch is actually smaller, just because of the percentages in the pipeline. So, but it's still a pretty significant gain to several of the machines. So hardware can be used for stretching. It can also be used for translation. This is a great way, as just the drag and drop. You can actually hardware accelerate that. You want to animate in and out of caching. OK, so to recap, basically we have the WPF effects library, which I highly recommend perusing and finding all the fancy things that you can do. The various PMs will blog within about other effects that we can use and enhance the Silverlight applications with. You want to look at the DX SDK if you want all the nitty-gritty details about HLSL, and the WPF build task if you want the more simple version. I'm going to recommend a couple of blogs here. Greg Schechter wrote the great series of blog posts on pixel shaders. Highly recommend reading. Mike Harsh, Mike is somewhere in the back, I think on the floor. He's raising his hand. He wrote the 3D spinning cube demo and actually has posted his source already available. So if you want to learn how to use projection, you can download his source, play with the samples. Joe gave a talk on Silverlight 3, what's new in it, and he talked about projection. And judging by his history, he generally posts things back to his blog posts pretty quickly. So no promises there, but I'll sign him up for it. And then myself, I will be posting around next week or the next 2 weeks. I'll be posting a lot of the samples that we saw today. One of the things that are going to be coming out in the summer is a book by our graphics architect covering both Silverlight 2 and Silverlight 3 features called Essential Silverlight, and it's published via, I think, Addison Wesley. So today we covered how we draw, our effects, projection, and hardware. And that largely concludes the talk. So thank you very much for coming. I appreciated having the chance to talk to you and share all of the benefits of Silverlight 3. Available for Q&A both offline and online. So there's a mic right here. And please fill out your speaker evaluations. We do read them, and I do consume all of the feedback. So appreciate it greatly.
Learn Silverlight 3 website, there's like a learning video on how to build pixel shaders. Yeah. And he uses a build method of resource instead of content for the PS file itself. Is there a reason to use one over the other?
So I think the main issue between resources and using it as a content is right now Blend only is, due to a bug in Silverlight, Blend is only able to consume the resources one. So I would suggest using that if you're going to use Blend, but we'll fix the bug.
Right. Another question is with, let's say you enable GPU hardware acceleration and you have it deployed and it runs well in your system, but it doesn't run on somebody else's system, and it looks like they have the requirements. Is there a way in code to tell that GPU acceleration is actually running?
This is actually there's a couple of complexities with evolving that API. So my guess is you not only want to, so not in Silverlight 3.
Okay.
When I do design it, I want to not only give you whether or not hardware acceleration was available at the beginning, but also if they hit something like out of video memory or max texture size, et cetera. Because then my guess is you're going to want to downsample your video or whatever you have there. So it's a great feature request. Make sure to pass it back. I'll pass it back to really myself, but
all right, thanks.
And I'll make a note. Thank you.
So actually I had a few questions. One of the problems I run into with WPF effects is that the only way to disable them is to null them out, and then if you have animations that depend on those, and you have to turn off the animations, and it's a lot of work other than just having a flag to disable that. Is there any intention of, I've heard that it's kind of like on the radar for WPF. Is it on the radar for Silverlight?
I actually haven't, so this is the great thing about betas is that you can give us feedback like this. Yeah, that seems like a more than complex thing that needs to be optimized out. I'll look into how to maybe we could optimize a blank effect or something like that.
So another question I had is just, it's more of a WPF question, I guess, is the projections that are in Silverlight 3, those seem to be a lot easier to use than using a viewport 3D. Is there any talk about moving those into WPF? Silverlight and WPF have written the spec together, and they've worked to make sure that WPF can implement them as well. So
the dev lead and the PM are actively working on it. As far as timeline for WPF, I'm not quite sure, but
Okay.
we can probably get that answer
Post 4?
post
Gotcha.
WPF 4. Okay.
So is there any limitations compared to the Silverlight version of the pixel shaders than WPF as far as, are they pretty much one-to-one? Can I take a WPF 1 and use it in Silverlight?
Yeah, you can pretty much copy the WPF pixel shaders back into Silverlight. The main differences, I think, they might take in a different number of variables, but I think that's about it.
Gotcha.
The other thing, of course, is that Silverlight compiles, parses, and JITs the pixel shaders into assembly code, which makes them fast, but they're not GPU based.
So one last question I had is you mentioned that, so correct me if I'm wrong, that if you have multiple Silverlight controls on a page, they all share a same UI thread, or they?
Yes.
Okay, so how far does that extend? Does that extend if you have multiple out-of-browser Silverlight applications running?
I would think not, but
Okay.
yeah.
So is it just the same page, or does it extend in the same browser to multiple tabs, or?
Oh, I see. So there are different. So there have been some changes to IE. I'll talk largely about IE 7.
Because the changes in out of process for each tab.
Yes. So for every process that IE hosts, there's one UI thread.
Gotcha.
And so if I think IE 8 is now doing per process maybe,
Gotcha.
there'll be more than one UI thread. So
Thanks.
It works it out. Sure.
Hi. Is there a way to get the hardware capabilities of the machine that the Silverlight control is running on? For instance, if you want to do different, if you want to different techniques, so you could scale back based on whatever. I mean, do shader models? I guess they still matter, right? So if you're running on a shader model 3 machine versus one that's shader model 2 or 4.
So Silverlight only supports Pixel Shader 2. So
okay,
that will be outright.
Solves that problem.
Yeah. In terms of the hardware capabilities, again, I don't know where the gentleman, he was sitting right next to you. He also asked the same question. What is your application, just so that
well, we're a game developer, and we traditionally, we haven't used Silverlight, but now we're starting to buy it, and just was one of the questions, if you could basically put shader effects on different objects on the screen, you always want to think, well, performance, what card does the machine have?
Right.
So you could.
WPF. So there's a couple of issues around the tiering capabilities, what I'll call that API. It was available in WPF, and it's basically what are the capabilities of the hardware that I'm playing on. There's a couple of security, sort of privacy concerns around it, and so we basically are not doing that in Silverlight 3, but I'll take them both in mind when I'm bringing back feature requests for Silverlight 4.
I guess what you could probably do is just run a test before, and track how long frames are taking. There's a way to do that, I assume.
That's a variable on system speed, though, so you can't really rely on that.
I'm sorry.
Yeah.
Sorry, you're.
No, I was saying that when you start your game or your app, I was wondering if you could actually just run a test very fast to see. There's a way to time.
There is actually an ability to query the frame rate. I'm not sure if Akshay is here, but there is a frame rate counter that you can actually query in-house if you want to do some basic perf tests, but you can ping Akshay afterwards.
Okay.
Yeah.
Thanks.
It's in the back.
Hello. How do you manage to enable hardware acceleration on both
I'm
Mac?
sorry.
Hardware acceleration. I'm French, because that's why. To enable 3D acceleration on both Mac and PC, are you using DirectX on PC, and what are you using on Mac? Or?
Oh, I see. So in order to hardware accelerate our Surface in Silverlight on the PC, we're using DX. On Mac, we're using OpenGL.
And are there any plan to enable acceleration in browser also in Macintosh?
Let's see, we have open threads with Apple to resolve the differences. They're changing how a couple of things work within their browsers. We'll try to get in-browser Mac support as fast as possible. It's definitely a high priority for us.
Okay. And last question, when you see the power of this new runtime, you maybe like to do some 3D gaming in the browser. Do we have any plan to have something to help developer to build game like XNA-like framework on top on Silverlight 3?
Well, so nothing that I know of in the Silverlight 3 timeframe, but we can take the request back. Yeah.
Okay.
So something on the books for maybe Silverlight 4, maybe.
Okay.
But if you send in feedback via the forums and your evangelists,
Okay.
we'll take into the request.
Thank you.
Thank you.
I got a quick question. Does Silverlight 3 support GIF transparency?
I don't believe so.
You don't?
GIF transparency? Yeah.
Just support PNG? Even in Silverlight 3?
Yes, and even in Silverlight, there's no GIF support.
I
Sorry.
think somebody wrote a third-party library that allows you to decode if you really wanted to.
Yeah, I think that there's a sample actually to do a decoding off of Joe's blog. So even I will link back. So the third blog on there, there's a sample on how to decode a GIF, but that's about it.
Okay, I'll check it out.
Thank you. Okay, well, thank you very much for coming. Have fun in Vegas. I'll see you guys all by the pool.